sample mean. So just as a refresher, so this is the weight of 17 pennies minted after 1982. If I want to estimate the population mean, okay, I have a sample. Do I know the true mean of the population? No. The best guess I could do would be to find the mean of my sample, right? How do you find a mean? Add them all up and divide by the total number. All right, add those numbers up. What does it add up to?
41.81.
And we would divide by
17. 2.46.
Give me one more decimal.
4.
Okay. So, if I found the mean of my population, I get 2.464 grams. If I took a different sample, would I get the same thing again? No. So again, we know this is not the population mean. It's not going to be the same as my next sample mean. So it's an estimate, but it's not perfect. If I want to be better at estimating, I would have to give a range of values. We would need a confidence interval. So we need to be able to do that same thing for the X bar. There is a slight change here. When we are dealing with the confidence interval for X bar, we are going to have to use what's called a t distribution. So the t distribution, you do have these formulas on your packet, I believe, yes. You're not going to be calculating this t statistic right now. We'll do that calculation more in chapter 10. But t is kind of like a z value in terms of you do your value minus the mean divided by the standard deviation. When we look at this, we're going to have what are called degrees of freedom with it. And the key thing that you need to know right now is whatever sample size you have, you'll have n minus 1 degrees of freedom. So if I have 17 pennies, I actually get 16 degrees of freedom. It's always one less than the sample size. Everything we talked about recently has been normal distribution. The t distribution is very similar to that. The difference is that degrees of freedom is built in, so the values vary depending on your number of degrees of freedom. Just like the normal distribution, it's centered at 0, so, and it's the same on each side, so it's symmetric around 0. Area under a curve is 1, because that's your total probability, so you would have half above and half below because it is all symmetric. It is going to flatten out and get close to 0, but not ever equal 0 exactly. So in terms of the graph, no, you can't really see this on yours. The normal distribution is this blue line. The t distribution will change depending on our degrees of freedom, but you see it's the same general shape as the normal distribution. Essentially what happens is as your sample gets smaller, it gets shorter and wider. We have more area out in the tails than we do in the center. We have a table for the t distribution, just like we did for the normal distribution. So it's on the next page. If you flip your normal table, the back of that is your t distribution. If you look at the top, this is one change for us. We know the normal distribution gives us area to the left. If you look at this table 7, and it has a picture of your t distribution, the probability in this table is actually area to the right. So it is the opposite of the normal table, but we can handle reading that. And if you forget, it's at the top of that page, so you can kind of remember which way it's giving us. So let's look at our problem. Let's practice figuring out how to read numbers off this table. If I want the t value, where the area under the t distribution to the right is 0.2, assuming 10 degrees of freedom. Okay, when you see this notation-wise, your subscript area to the right is 0.2. My degrees of freedom, I told you, was 10. So if you look on your t distribution, your rows, we have these degrees of freedom. So we want to go down to 10. And at the top, it has probabilities. Okay, so we want the probability is 0.2, so we go over to the 0.2, and what's the number there? 0.879. I want to make sure how the normal table is set up. Degrees of freedom are here. These numbers at the top, these are actually the areas in this table, so those are the probabilities. So we had 0.2, 10 degrees of freedom, so my t value is 0.879. All right, so everybody see where I'm getting that? Okay, let's try another one. So I want the t value so that the area to the right is 0.1, and we have 15 degrees of freedom. So my t is 0.1, degrees of freedom is 15, so we get 1.341. This is symmetric, so if I asked you to find t, so the area to the left is 0.1 with 15 degrees of freedom. So same problem we just did, except I flipped it. So we know the table gives us the area to the right, and we found that when this is 0.1, this t is 1.341. So if I wanted area to the left to be 0.1, remember this whole thing is centered at 0, what do you think your t would be? Okay, so if I ask you for the area to the left, or for the number on the left side, you just use your table and then you put a negative on it because they're opposites. Okay, so let's talk about the confidence interval for this. We will deal more with this t value in the next chapter, so I'm not really giving you a ton of detail about how it's calculated. We just really need to be able to use the table right now. So when we have the confidence interval, we still have some things that we need to worry about. So we have to have, data from a simple random sample, less than 5% of the population. It should be normally distributed, or the sample is large, when we're talking about X bar, how big does it have to be if it's not normal? Yeah. So same as criteria for X bar, either the sample has to be normal or our sample size has to be bigger than 30. So then the formula for this confidence interval, it's very similar to when we did the formula for the p-hat confidence interval yesterday. So if you look on your formula sheet, under chapter 9, so the first bullet is the confidence interval about p-hat. And so it was p-hat plus or minus a z times our standard deviation for p-hat, essentially. The one right underneath it is confidence interval for the sample mean. And so it's x bar plus or minus, we have some t value times essentially the standard deviation for x bar. So this is right here, again, we're really just plugging in the formulas. Where the t comes in is you have to be able to read it from the table. All right. And we can also do this one on our calculator. So when we do this one, we will go to Stat, Tests, and it is number 8, T interval. And so I will show you how to do it by hand as well as on the calculator. My expectation, just like with yesterday, I said on the homework, make sure you do a couple by hand so you can. Then you can do the calculator for the rest. So same idea with these. We want to make sure we can do it by hand, but we'll also rely on that calculator a lot. So let's look at this one. So this data shows miles per gallon from a Ford Focus with 16 different owners. Treat the sample as a simple random sample. Construct a 95% confidence interval for the mean miles per gallon. Interpret this interval. All right, would this be one that you think would be easier to do by hand or on the calculator? Our formula for by hand is x bar plus or minus p alpha over 2 times the standard deviation over the square root of it. We can get all of that stuff, but I'll have to calculate the x bar. We would also have to find the standard deviation, right? Which we would probably do on our calculator. So if we're going to go ahead and use the calculator to do the standard deviation, we might as well do the whole thing on the calculator. So what I want you to do first is put all of this data in your L1. So clear out whatever is there and type in these points. Okay, everybody have those entered? So next we are going to go to Stat, Tests, number 8, the T interval. All right, this one asks us a few different prompts. We have the option of doing our interval from data or from stats. Data is the scenario where we typed all of our points into L1. Stats would be the scenario where in the problem it said X bar is this and S is this. So we have data here, so make sure data is selected. The list, that's asking you where your data is stored, so that should be L1. Frequency is 1. We're not repeating any of these. Confidence interval, I wanted 95%, so 0.95. And then we can go to calculate. And so it gives us 0.35, 0.246 to 38.354. That's my confidence interval. I asked you to interpret, so that's tell me what this means. So it was a 95% confidence interval, so we are 95% confident. This was talking about the sample mean, so we could say the mean is between 35.246 and 38.354 miles per gallon. So we're 95% confident your average miles per gallon will be somewhere between these two numbers. Any questions on that one? Everybody got to work on their calculator? I might illustrate how to do that one by hand, just to kind of show you. I think I put a blank slide next to it anyway. So if I wanted to do this one by hand, in order to do the by hand, we have to have the mean and standard deviation. So if you put in your data, you could go to calculate one variable statistics like we did way back when. Your list should be L1. Frequency list, don't have anything there. Hit enter. So my X bar is 36.8. Standard deviation was 2.917. Okay, so then if I wanted to use the formula, we have to have our T alpha over 2. All right, so we are talking about a 95% confidence interval, right? So we want 95% to be here in the middle. So how much is left for the ends? 5%, and you split it up over the 2, so you get
2.5 each.
Each end would be 2.5%. Okay. So my degrees of freedom, how many sample points did we have? 16. It's n minus 1, so it would be 15 degrees of freedom. So you go to your table. We're talking about a T, so you go to the T distribution. 15 degrees of freedom, the probability across the top should be 0.025. We'll get 2.131 for the T value. Did everybody find that? So then it's just a matter of plugging into the formula. The formula on our formula sheet is X bar plus or minus T alpha over 2 times S over the square root of n. We have everything. X bar is 36.8 plus or minus T alpha over 2, so 2.131. Standard deviation, 2.917. Divided by the square root of n was 16. And then you just plug that into your calculator. So I usually do the minus first. And then if you hit second enter, you can just change your minus to a plus. And then we'll do the exact same thing that our calculator gave us. So we're going to do another one. Again, I'll probably show you both ways, by hand and on the calculator, just so we're comfortable with that. So this time I'm asking for a 99% confidence interval about the population mean. So the population mean, I'm talking about the mean, so that's what's telling me I'm using the x bar, not the p-hat. Again, I gave you the original points. If I didn't, I would say like when x bar equals this and s equals this. So first step would be to put all of those points in your calculator under your L1. Did everybody get that? If I asked you to interpret it, we would be 99% confident that the average weight of a penny is between these two numbers. Let's just talk if I had to do it by hand. So you would have to have your x bar and your s, which we can get from our calculator. So if we calculate one variable statistics, x bar is 2.464, standard deviation 0.0177. My n, how many pennies did we have?
17.
So how many degrees of freedom would we use?
16.
So the T alpha over 2. If we're talking about 99% confident, so we have 99% here in the middle. So that leaves 1% to split up over the two n's. So each n gets half a percent, so 0.005. So go to the table, 16 degrees of freedom, the probability across the top, 0.005. And we get 2.921. So then you plug into the formula, x bar plus or minus T alpha over 2 times the standard deviation divided by the square root of n. This time, it's not an exact match to my original, but it's very, very close. We don't see a difference until that fourth decimal place. But that is why it's important for me that you show me how you're getting there. You know, when you're calculating standard deviation, write down what it is so I know how many decimal places you rounded that standard deviation to, because rounding that differently will change this. So just make sure you're writing down everything if you do one by hand. Any questions there? Okay, so last thing with this, just like last time, we figured out, basically I didn't show you where it came from, but it just from reworking the formula, how big a sample would have to be under certain conditions. So I could ask you a question along that line if I wanted to know the sample size required. Again, that is on the formula sheet. So under sample size, the first bullet was with the population proportion. The second bullet here is for the population mean. So the number required, this one, it does deal with the Z, not a T. So Z alpha over 2 times standard deviation divided by the error squared. So we'll try that with one of these and then I'm done. So if I want to go back to estimating my mileage on the Ford Focus, how large of a sample would be required to estimate the mean within 0.5 miles per gallon with 95% confidence? So my Z. 95%, is that one of the common ones that it gave us? Yeah, that critical value is given at the bottom of our normal table. It tells us 1.96. We could always look it up inside the table like we did yesterday if needed. So I have my Z. Standard deviation, we did this in, let's see, a couple examples ago. So let's pull that standard deviation from this one. When we did standard deviation, it was 2.917. All right, my error, how much error am I allowing? 0.5. We want to be within 0.5 miles per gallon. So then my formula, N equals Z alpha over 2 times S divided by E squared. So we plug in our values. Z alpha over 2 is the 1.96 times the S, 2.917, divided by 0.5, and then we square. So I got 130.75. Again, if you rounded your standard deviation differently, you could be 131 point something or 129 point something. So please just make sure you're writing down the numbers you're using so I can check that. So would 130 people be enough? No. So we must have 130. So we always have to round up in this scenario. Any questions for me? So we've got a little time right now. You also have the whole class period tomorrow.